let's start with the seminar. It's a great pleasure and honor to have Professor Mike Doherty from University of California, Santa Barbara. Very big name in the area of chemical engineering, and you would know I would not be doing justice because I'm a mechanical engineer, happen to be in the petroleum engineering department. But I'll try to read out all his accomplishments, and I've heard a lot about Mike Doherty from Professor Nandakumar through our discussion planning about EPIC and how we should be bringing out exemplary speakers like Mike Doherty to our campus. So Professor Doherty, he received his bachelor's from Imperial College London and PhD from University of Cambridge. And his pioneering research spans multiple areas of chemical engineering, recent focus being on process intensification and innovation. That also happens to be one of the focus areas for EPIC. In the areas of separations with chemical reactions, crystallization of organic materials, and protein synthesis, and conceptual design of chemical process systems. Amongst his recent accomplishments, he has recently been elected to the National Academy of Engineering, and he has received E.V. Murphy Award for Industrial Engineering Chemistry from ACS, and he delivers Stanley Katz Memorial Lecture at City University, New York, Roger Sargent Lecture and Centennial Lectures at Imperial College London, and Darsharma Lectures at Institute of Chemical Technologies, Mumbai. So it's a longer list actually, but without getting into further into his lecture time, let's welcome Professor Doherty and enjoy his talk.
Thank you, Mike. It's a great pleasure. I'm going to start by partially undressing just to be more relaxed, if you don't mind. It's really a great pleasure to be here. I want to thank you for the invitation, and to Mayang and Dimitri, who have entertained me so well the last day and a half or so. What a beautiful campus you have. You should be all feel very proud. Is there a problem?
Remember to get on stage to get properly voiced.
Okay, thank you. Is that better now? Okay.
You have to stay in your cage.
Thank you, Dimitri. I'll remember that. What a beautiful campus you have. And I would say to the students, you should really feel proud to be here. I've certainly enjoyed my time here, and I imagine you must be as well. So, today what I'm planning on doing is telling you a small sliver of things that we do in my group in the general area of process engineering. And for most of my career, or at least a big chunk of my career, the work we did was focused on chemical industry, oil and gas, vapor-liquid systems, separation systems involving liquids and vapors. And about 15 years ago, I decided to change and do something different for the second half of my career. So what I'm going to tell you about today is some of those things that we've done in the area of particle technology and crystallization over the last few years. So many of you will recognize this photograph of the Taj Mahal. I'm not pandering to you. I am showing this as one of 2 or 3 photographs I like to show as inspiration for what we do in chemical engineering. If such a wonderful building can be constructed by humans, I find that inspirational for the kinds of things that we're trying to do in technology. Before I begin the lecture, I would like to make some acknowledgments because, of course, I don't really do any of the work. All the work is done by you, and maybe your advisors and me can take some credit for having some broad oversight, but the real work is done by the students. And these are the students that I've had in my research group since the very first one in 1999 in this area of crystallization. There's an even longer list of students prior to 1999 who used to work on other topics that I'm not showing. And of course, not only do you need smart people to do this kind of research or the kind of research that you do, you also need money. Groceries and lodging and occasionally some entertainment. And this is the list of companies and agencies who provided us with funds over the years that enable us to do the work. So you might ask, why crystals? And if you think about it, crystals are everywhere. Every pharmaceutical tablet that we take is composed of very small amount of crystalline drug, milligram levels, very small amounts. Most of the tablet is excipient, cellulosic materials and so forth. Otherwise, the tablet would be almost invisible. There's so little drug that you take in a dose. Of course, crystals come up in ice cream, in foods, catalysts. They're all over our everyday lives. And the drug industry alone, worldwide, has revenues in excess of $1 trillion. And if you take into account all of those other industries that I just mentioned, the total is in the several trillions of dollars. Does anyone know? Faculty aren't allowed to answer any of my questions, just so we put that out there right now. Does anyone know what the GDP worldwide is, what the global GDP is? Do we know what it is for the United States? How many? Very good, 17 trillion. So globally, it's about 72 trillion. So $2 or $3 trillion that crystals are responsible for is a significant fraction of the world's GDP. So that makes it an important problem to work on. The kinds of things that my group does go from the molecular, and in fact, probably 2/3 of my group work on molecular modeling of crystal growth mechanisms, which I'm not going to talk about today, to create models of crystals and how they grow, through the process level, process systems engineering. This is the level that I am going to talk about today, all the way through to formulation engineering, whether it's of a foodstuff or tablet. So here we have some pharmaceutical crystals that a friend of mine at Merck gave me this image. And you'll see that they come in all shapes and sizes. So here's a nice equant-shaped crystal. And drug companies like this kind of crystal because if you can grow them to the right size, which would typically be on the order of 50 microns, if you can do that, that's very good for tableting. You'll get very uniform dosage in each tablet. And that, of course, is absolutely vital. The dosage in a tablet should not be sometimes 10 milligrams, sometimes 5, other times 15. When the dosage is supposed to be 10, it's better be 10 plus or minus like 1/10 of a milligram every time. So when the crystals are grown into equant shapes like this, it's very easy, well, it's not easy, but it's easier to do the dosage. These rod-like crystals are the next best kind of crystals that you can grow for pharmaceuticals, and the needles are the worst of all. And the mantra in the pharmaceutical industry is, for God's sake, don't grow needles. And of course, guess what kinds of crystals most commonly grow in pharmaceutical manufacturing? Almost always you get needles. It's just, nobody knows why, it's just the perverse way of the world. And so, one of the important things that the drug companies are interested in is how can we engineer the crystal shape. As I say, that's not something I'm going to talk about today. That's the usual thing I talk about. But today I'm going to talk about two other aspects, polymorph and size. So what's interesting about crystallization that distinguishes it from, say, distillation or absorption or other types of separations is that there are many tasks that the crystallization task is intended to fulfill. There's all these tasks about purification. But in addition, crystallization is a particle formation task. And so you're interested in the size of the particle as well as the size distribution. And we're also interested in the shape of the crystal. Are we going to grow needles or plates or more equant-sized crystals? And finally, perhaps in some respects, the most important of all is what polymorph do you grow? And what is a polymorph? Solids form different lattices as they crystallize. The simple ones that you will have all heard about are things like BCC, FCC, and so forth. But there are many other different types of lattices, and pharmaceutical crystals almost always grow into the other less symmetric lattices, monoclinic type lattices, for example. Very rarely do pharmaceutical crystals grow into very symmetric lattices like the cubic lattices. Well, when the atoms or molecules crystallize into one of these lattices, there are often multiple choices. And some lattices that the crystal can grow into will have higher energy. Other lattices will have lower energy. And the different polymorphs correspond to the different lattice structures. Only one of them, of course, will be the globally minimum energy lattice, and that is the most stable polymorph. But frequently there are 2 or 3 or 4 or sometimes 10 other kinds of lattice structures that pharmaceutical crystals will grow into, and it becomes really important to know what polymorph you're growing. And I'll tell you why in a minute. But before I do, let me tell you a few things about size. The size of the particle that you want to make depends critically on the application. If you are making an injectable drug, then the drug particles have to go through a hypodermic syringe, and clearly the particles need to be very small. So for injectable drugs, a typical particle size might be 200 or 300 nanometers in diameter, or in length, in characteristic length scale. For inhalable drugs, you're sniffing it, you can have larger particles, 5 microns. For formulated drugs that go into tablets, maybe 50 microns is a good size. If you're making a commodity chemical like adipic acid, then maybe 400 microns is a good size. Table salt, for example, is about 300 microns. Those particles are about 300 microns in characteristic size, just so that you get some feel for the numbers that I'm talking about. So let's spend a minute talking about polymorphism. But as you know, as I'm sure you know, carbon comes in 2 different forms: graphite, or charcoal, and diamond. Absolutely the same stuff inside. It's just carbon atoms, elements, connected in a different bonding structure, connected in a different crystal structure. The first discovery of polymorphism is attributed to Michael Faraday, who in the 1820s was more or less an apprentice to Humphrey Davy. Michael Faraday eclipsed him subsequently to become one of the great stars in chemistry and physics. But at the time, Michael Faraday was Humphrey Davy's sort of right-hand man. And they were traveling through Italy, as one does, visiting the Duke of Tuscany, who knows why. And the Duke of Tuscany, being a very rich man, did the kind of things that lots of rich people like to do, which is show off their wealth by doing crazy things that nobody else can afford to do. So the Duke of Tuscany had a telescope, an observatory. And what he liked to do was turn the telescope around at midday so that the telescope took the rays from the sun and magnified them through the telescope to create an intense beam of heat on a surface. And he liked to put diamonds in the focal point of this beam and burn the diamonds. Right? So they were doing this one day, and Michael Faraday had a really smart idea. He collected the gas of the burning diamonds and discovered it consisted mainly of CO2. And that he already knew that if you burn charcoal, it gave CO2 as the gas. And on the basis of this and some other observations that he made, he was able to state a preliminary observation that diamonds and charcoal consisted of more or less the same substance, and that they were just different crystal forms of the same thing. So that's how polymorphism was first discovered. And over the last 150 years, it's become well understood how important this phenomenon is. And let me show you the phase diagram for carbon. So this is the pressure axis. This is a pressure-temperature phase diagram like we've seen so many times for normal substances, like water and so forth. Temperature, vapor pressure. And you'll see that under all normal temperatures and pressures, graphite is the stable phase. Diamond is the metastable phase of carbon. So if we wait long enough, all diamonds will eventually turn themselves thermodynamically into graphite. But probably not in our lifetimes. The reason this is important is perhaps easily understood from the diamond and graphite example, which is why I like to use it. You can hardly think of two substances less similar than diamond and graphite. Graphite's one of the softest solids known. Diamond is the hardest solid known. Diamond is a semiconductor, graphite isn't. And what you find as you look at different polymorphs of different materials is they have completely different properties. Color, hardness, bioavailability, which means how well they dissolve inside the body, mechanical strength, shelf life. You know, chocolate's an interesting one. If you buy a piece of chocolate that's been sitting on a shelf for a long time, it looks like it's moldy. It has that white, mold-like looking layer on the surface. It's not moldy. The fats in the chocolate have just turned into a different polymorphic form of the solid. So what you're seeing in that white haze on the top of chocolate is a different polymorph of the triglycerides that are in the chocolate itself. Different polymorphs have completely different shapes. So this is a protein called a protinin, and the metastable polymorph are the needles, and the more stable polymorph are these bipyramids. And if you put this protinin in a solution and let it sit there, and you supersaturate that solution, crystals will form, and initially both polymorphs will form together, like you're seeing on the left, and over time, the less stable polymorph, the needles, will transform into the more stable polymorph, and at larger time, you won't see any needles at all. All you see is the most stable phase. And this has been done countless times in countless different systems, and it's really well understood. And finally, this is all by way of introduction. I'm going to actually tell you something new in a minute, I hope. I'm going to focus a little bit on modeling and computation. This, after all, is an epic seminar, but I should at least address some of those issues. I have to tell you, it will not be CFD or all of the other interesting things I've heard about today, because I don't do that. But it's a different kind of modeling, but in the same space as CFD and so forth, in the sense that you end up with partial differential equations, and they need to have methods of solution, and so on and so forth, which we're not going to dwell on, I should warn you. So this is a friend of mine, Jim Traynor. He used to run a very big modeling group at DuPont, and he used to have his elevator pitch to justify why this modeling group was important. You've all read it now. I don't need to read it to you. And that was his mantra, that if you don't understand your process, if you can't model your process, then eventually the competition will eclipse you, and eventually you'll be out of business. And I think that there's a great deal of truth in that. The pioneer in chemical engineering of process systems engineering was a fellow called Roger Sargent at Imperial College. Roger's family tree now consists of more than 1,000 PhDs. And Professor Ramagnoli is one of them. He worked for George Stephanopoulos back in the 70s, who worked for Art Westerberg, and Art Westerberg worked for Roger Sargent. I'm a member of that family tree, second generation. I worked for one of Roger's PhD students, John Perkins, who worked for Roger, was my advisor. And so it goes. I don't know. It's up to Chris Ludus, Ignacio Grossman. I mean, there's a ton of people in this family tree who all go back to Roger. And as I said, there's more than 1,000 PhDs in this family tree right now. I was going to say fortunate. Maybe I should say unfortunate enough. Fortunate is the right word, but man, this was an enormous amount of work. To be a co-editor of a special Festschrift issue of AICHE Journal in the September 2016 issue to commemorate Roger's 90th birthday, which came a few weeks after that. And Ignacio Grossman and I spent the best part of the last year putting together the 55 papers that appear in this journal. And you really start to learn who your friends are when you do something like this, because everything is on like a super fast time schedule, and some people respond and many people don't, and you find yourself on your knees begging people to do things like by tomorrow. And so that was in itself a very interesting exercise. But most of us in this business in chemical engineering can trace our roots back to this man. He really is incredible intellect. Okay, let me now tell you about polymorph selection. So I've got two topics I want to talk about in, say, the next 30 minutes. One is how to get the polymorph that you seek out of a process. And then the second one is, once you've got the polymorph that you want, how can you figure out what range of particle sizes are attainable within the process that you've designed. So those are the two key things I want to talk about with you. So firstly, let's talk about polymorphism. In a batch process, so the focus here is on the pharma industry, and as I'm sure you know, most pharmaceuticals are made by batch processing. And why is that? Because they're typically small volume products, and because many of the early processes were invented by chemists. And chemists think about things batch-wise. Chemical engineers think about things continuous-wise. So most pharmaceuticals are made by batch processing. The pharma industry is trying to change that right now. And my prediction is over the next 10 or 15 years, most pharmaceuticals will in fact be made by continuous manufacturing. It might only be a bench-scale continuous process that does the world's supply of any particular drug. But you've got so much more control of a continuous process than you do of a batch process. It eliminates the batch-to-batch variations and so forth. That there's a huge push right now in the pharmaceutical industry to adopt standard chemical engineering practice of continuous manufacturing. It turns out you can do things that nobody realized this until very recently. You can do things in continuous manufacturing that cannot be done by batch. And one of those things I'm going to show you right now, and it's this business of polymorph selection. So here's how a batch process works. This is a phase diagram, a solubility curve for some solute in some solvent. So we all know from our kitchen experience, you can put so much salt into water at any particular temperature and dissolve it. And beyond that, the excess salt comes out as a precipitate and will sink to the bottom of the pan, right? Same with sugar, same with everything. So you can capture that concept in a diagram of the concentration of your solute in solution as a function of temperature that you're doing the experiment at. So imagine we've got L-glutamic acid. Never mind what L-glutamic acid is. It's a 5-carbon dicarboxylic acid with an amino group on it. So it's an amino acid 5 carbons long. The alpha form has a certain crystal structure, and it's metastable. So what you have to keep in your mind for the next 4 or 5 slides is alpha, for this problem, alpha is metastable. The beta form is the most stable. How do we know? And this is the saturation curve for the crystal alpha form that has its particular crystal structure. This is the saturation curve for the beta form. So I pick a temperature, maybe 23 degrees C, and I start off at a certain concentration of L-glutamic acid, somewhere around 20 grams per liter of solvent. The solvent is water. And I keep my experimental apparatus, I keep my crystallizer fixed at this temperature, and I just let it sit there, and I watch what happens. And what happens is, the solution is supersaturated, so crystals necessarily will form. That's what happens in supersaturated solutions. And initially, you will typically get both types of crystals, the alpha and the beta. There might be a predominance of alpha, and as these crystals come out of solution, the solution concentration goes down, right? So as the solution concentration is going down and the crystals are crystallizing, you're following a path from the initial condition down, 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 down till you get to there. When you get to there, you continue to drop because you continue to make the beta crystals, and suddenly you find yourself with a solution concentration like there or there. Now, students, what happens when I get to there? What happens to the alpha form crystals? Do they grow or dissolve? We could have a show of hands. Should we have a guess?
Reorganize.
What?
They start reorganizing.
And do they get bigger or smaller?
They get smaller.
They get smaller. Why is that?
The rate is sorting into the solution.
Precisely, they're dissolving. When the crystals find themselves, when the alpha crystals find themselves in a solution of this concentration, they're below the concentration of their solubility curve. What happens when you put a crystal, in the extreme case, into pure water? It dissolves. Well, anytime a crystal finds itself in a solution that's undersaturated, necessarily the crystal dissolves. So when I drop below the saturation curve for alpha, all the alpha crystals start dissolving. What happens to the beta crystals? They're still growing. So what's happening in this regime here is the alpha crystals are dissolving, the beta crystals are still growing, and the beta crystals will grow until the solution concentration gets to that point there, and then what happens? Everything stops. The crystals and the solution are in thermodynamic equilibrium, and you have a crystal phase and you have a solution phase with equal chemical potentials, and you have just crystallized out of solution all of the crystal mass that's possible to crystallize out at this temperature, and the entire experiment is over. It just will now sit there for eternity at this particular temperature, that particular saturation concentration, with this much mass of crystals that crystallized out from the initial concentrated solution. Everybody with me? This is called solution-mediated polymorphic phase transformation. Very grand thing, but all it says is the metastable crystals dissolve, the stable crystals grow, and that's all she wrote. That's what you get. So you, in a batch manufacturing operation, this is always what happens. And if for some reason you wanted the alpha crystals, really difficult, more or less impossible, to get them by batch crystallization. So, about 8 months ago, we were rummaging through the literature, as one does, and we came across this paper that came out of Alan Myerson's group at MIT, and it was an experimental paper. And in this experiment, they had L-glutamic acid growing in a continuous crystallizer, not batch. So a continuous crystallizer is like a continuous reactor. You have a tank and a stirrer. Supersaturated solution comes into the tank. It sits in the tank for a certain residence time. During that residence time, some of the solute crystallizes out, forms crystals, and there's a continuous exit of both crystals and slightly desupersaturated solution in the exit pipe, and you've crystallized out a certain mass of crystals continuously, and if the crystallizer has a longer residence time, you get more crystals and bigger crystals, right? So it's very much like a chemical reactor, stirred tank chemical reactor, except instead of chemical reaction happening, you've got crystallization happening. So this struck us as a really odd result. So they seeded this continuous crystallizer with the most stable phase, the beta phase of glutamic acid. I can tell you with 100% confidence, if this were a batch experiment and you had a supersaturated solution of glutamic acid and you seeded that solution in a batch experiment with the most stable phase, all you would get is the most stable phase crystals. That's it. And that's what happened here too. You'll notice that the most stable phase crystals, the beta phase, are present up to 200 minutes, 3 hours. And the alpha phase, the most stable, the least stable phase, has 0 concentration of the alpha phase. And if they stop the experiment there, which any sensible person would have done, because clearly it's lined out to a steady state, right? And this is clearly nothing is happening there. Any sensible person would have stopped the experiment right there and declared continuous crystallization is just like batch crystallization, as we all suspected. But for whatever reason, they decided to carry this thing out for 10 hours. And over later times, lo and behold, the most stable crystals start to disappear. And after 10 hours, there's none there. The least stable phase starts to grow. And after 10 hours, that is the only solid phase that comes out of the crystallizer. So this makes no sense. Can't happen. We read this paper and I said to one of my students, you ought to form a simple model of a crystallizer and show that this is all bullshit and this can't happen. There's something wrong with the experiment. Their XRD is wrong. Something is wrong here, and we'll figure it out. So clearly we didn't find that, otherwise I wouldn't be here telling you about it. So we formulated this simple model. Those of you that know about crystallization will recognize immediately that this is the standard model for a continuous stirred tank crystallizer. N represents the population density of crystals. G is the growth rate, the linear growth rate of the particles. Tau is the residence time in the crystallizer. Alpha and beta are the two different polymorphs, so you do this for the alpha phase and the beta phase separately. You need a material balance to make sure that all of the stuff that gets sucked out of solution is properly accounted for. You need a growth rate, which we take to be proportional to the supersaturation to some power, GI. You need a birth rate or a nucleation rate, which we also take to be proportional, different proportionality constant, to the supersaturation to a different power. And typically in a continuous crystallizer, you have secondary nucleation because the particles are being beaten up by the impellers and little fragments are formed, so you get secondary seeds as well as primary nucleation. So there's a term here that accounts for the mass of the crystals in the nucleation law. You need some boundary conditions that everybody knows about. So if you know about crystallization, you look at this and you go, looks fine. If you don't know about crystallization, never mind. This is not the place to learn it. So what we do next, to the students, what's the first thing we always teach you when you develop a mathematical model? Put the damn thing in dimensionless form, right? There are parameters everywhere. Too many parameters for any of us to figure out how each one is going to affect the dynamics and the steady state of the ultimate performance of this model. If you don't put it in dimensionless form, you are totally lost right out of the gate. So you put that model in dimensionless form, and all of those parameters get reduced to 3 dimensionless groups, only 2 of which are really important. Who knew that? Turns out there's a Damkohler number for the alpha phase. The Damkohler number is the ratio of the characteristic process time to the characteristic growth and nucleation times. There's a similar Damkohler number for the beta phase. And then there's this gamma parameter, which is to do with the driving force, the saturation and concentration of the beta phase and the alpha phase and so on that comes in various places. But the 2 key parameters are these Damkohler numbers, which are ratios of characteristic times. Process time to nucleation and growth time. So you make the thing dimensionless, and I'm not even going to show you. Showing you any more equations is a total waste of time, right, at this point. If you want to know more, you have to go read the paper. What I want to show you is what happens as you go through all of the traditional steps once you've got this model. It's got 7 ordinary differential equations in 7 different states, 3 moments for the alpha phase, 0, 1, 2, 3 moments for the beta phase, 0, 1, 2, plus the mass balance, 7 states. And we do a linear stability analysis on that model. So you've got 7 nonlinear ordinary differential equations. You linearize them about the steady state. You do an eigenvalue analysis, and we use a Ruth table test. It's not exactly the Ruth table test. There's a different version where you only have to do half the work, which is usually a good idea. So we use a Ruth-like table test. And lo and behold, at the end of all of this, you can actually get analytical expressions for the eigenvalues in this model. And so you can tell exactly when the steady state is going to be stable and exactly when the steady state is going to be unstable. And in the parameter space, turns out there are 3 steady states, and each one is stable in only one regime in parameter space. So there's a trivial steady state where nothing happens. The supersaturated solution comes in, and the supersaturated solution leaves at exactly the same concentration with no crystals. And that steady state corresponds to when the volume in the crystallizer is really small. So when the volume is really small, nothing happens, and there's a trivial steady state, and it's stable. That's not surprising. That happens when these Damkohler numbers are each less than 1. When the beta Damkohler is bigger than 1, and is also bigger than the alpha Damkohler, so there's a straight line slope 1, it turns out in this yellow regime, the beta phase, which is the thermodynamically stable phase, also corresponds to the stable steady state. Now we're distinguishing between 2 kinds of stability. Dynamic stability in our apparatus and thermodynamic stability. And it turns out that in our apparatus, in our crystallizer, there's a regime where the thermodynamically stable phase is also the dynamically stable steady state. But what's really interesting is there's a big regime where the metastable solid is the dynamically stable steady state. Now, we weren't expecting this at all. I expected the entire diagram to be yellow. So when this happened, I'm like, wow, doesn't seem possible. Go back, I asked my students, go back and look at all of the experiments you can find in the literature where people have done this kind of thing, and stick those experiments on this diagram, and let's see if there's any relationship between them. And sure enough, we found two sets of experiments. One for L-glutamic acid, that's the set of experiments that drove us to do this in the first place. Those are the diamonds. And para-aminobenzoic acid, those are the squares. So let's look at the diamonds. There are 4 experiments that were reported in that paper where the metastable solid phase comes out as the stable steady state from the crystallizer. And you take the experimental parameters reported in the paper, volume of crystallizer, flow rate, temperature, all of that stuff, you put them into R conditions, and lo and behold, all 4 experiments lie correctly in the blue side. And then there were 2 experiments where they changed the conditions in the crystallizer, and the thermodynamically stable phase came out. Sure enough, they lie in the correct region of our stability diagram. And then for para-aminobenzoic acid, same thing. A bunch of experiments. These are the squares. The filled yellow are where the stable phase comes out, and then these are where the other phase comes out. So there's like 14 data points here, experimental data points, and every single one lies where the theory tells you it should lie. So suddenly we were converts. We started off doing this thinking we were going to show that something was wrong with the experiments, and in fact what we ended up confirming is that a continuous crystallizer is capable of producing long-term, at steady state, thermodynamically metastable solids. And to the best of my knowledge, prior to these experiments that Alan Meyerson and his team did in the last couple of years, and prior to this analysis that we did, this was completely unknown. And it opens up all kinds of opportunities in the pharma industry, and some other industries too, which I don't have time to mention to you, where we also have got some projects going now, where continuous manufacturing allows, in principle, to get solids that you couldn't otherwise create by a traditional batch process. The final slide in this set of slides I want to show you is a sanity check we did on our model. Clearly, if you make the continuous crystallizer have a very large residence time, you would expect it to ultimately give you only the thermodynamically stable phase as the product. And in fact, that's exactly what happens. We take one of the points, experimental points, which had a residence time of 1 hour, where the metastable phase was the observed and predicted phase, and then we just dialed in to our model a longer and longer and longer residence time, and by 10 hours, if not before, by 10 hours, the curve always ends up in the thermodynamically stable side, completely in line with intuition. And in fact, you can prove that this will always happen. You can go to the model and prove that if you take such a path and increase the residence time, you will always end up on the thermodynamically stable side of the diagram. And so that's a nice, pleasing sanity check on what went on. So the summary of all of this is simple. Milton Friedman. Who's heard of Milton Friedman? Milton Friedman, right? He's an economist at the University of Chicago. And economists are always criticized for having overly simplified models. And some chemical engineers are too, like me. I like simplified models because they're the only models you can ever understand. And one of the things I love about Milton Friedman's justification of his simple models is a statement he published a few years ago. It goes something like this. The quality of a model should be judged not by the reality of its assumptions, but by the quality of its predictions. And what I'm showing you here is a simplified model that is clearly not true. This model assumes that you've got perfect mixing in the crystallizer. You will never have perfect mixing in the crystallizer. And it assumes a number of other things like that that are obviously not true. But the beautiful thing is, it's simple enough to expose all of the characteristic features of what's going on in this device, so you can learn something useful, and once you understand that useful thing, you can start to configure continuous processes to exploit that knowledge that you might never learn had you started off with a monumentally complicated mathematical model that had more physics in it, but which you could never understand anything as simple as what I've shown here. So I'm a big believer in simplified models. Let me show you very quickly in the last 10 minutes some other aspects of what can be done using these kinds of models. So you can use batch crystallization. You can use continuous crystallization in these so-called mixed suspension, mixed product removal crystallizers, which are like stir tanks. You can do crystallization in a plug flow crystallizer that's the analog of a plug flow reactor. And it turns out you can model all of these different devices with a cascade of continuous stirred tank crystallizers, and you can learn something about the behavior of all of these different devices by looking at a cascade model of these things. I'm not going to drag you through, I mean that's a more schematic version of what I'm talking about. One goes to the next, goes to the next, goes to the next, and you can carry this along as long as you like. But the question that we're interested in asking is, if I specify the type of device that I'm going to implement, a cascade with one crystallizer, that would be the single stirred tank crystallizer, 2, 5, 10, 50 is like almost the perfect plug flow device, which is equivalent to the batch, just like a plug flow reactor and a batch reactor are the same thing. If you have enough of these cascade crystallizers, you can model plug flow crystallizer, and therefore you can also model the batch crystallizer. So if you specify the crystallization chemistry, and by that I mean what's your solute, what's your solvent. If you do an anti-solvent crystallization, you need to tell me about that as well. What are the solubility curves and kinetics and so forth? If you know about these things, then the question is, what is the entire range of particle sizes that you can get out of that device? So that these are called attainable regions, and they're very popular in reactor engineering, but nobody ever applied the concept to crystallization until we did a year or two ago. And I just want to show you what you get when you do this in crystallization. You get some very interesting results. So again, same model as before. The mass balance disappeared somehow with my slide hiccup. So there's a mass balance there that we don't care about anyway. Nucleation and growth kinetics just like before. So it's the same model as before. And we're going to interrogate this model. And the way we're going to interrogate it is by, as I said, by having a cascade of crystallizers. And in this case, I'm just going to give you an example of 3. So we start off with an initial concentration of something like, let's say, 400 or so grams per liter of solute. And in the first crystallizer, we're going to hold it at this temperature, some temperature around 330. That's the inlet concentration into the crystallizer. The stuff sits there for a certain length of time. It sucks out a certain amount of solute from the solution. And the outlet from the crystallizer, of course, the solution is at a lower concentration. And you sucked out this much mass, the unit volume, which got turned into crystals. That outlet, at this temperature, you now cool down, and you have a second crystallizer with this inlet concentration. And it sits there for a certain length of time, residence time. It sucks out a certain amount of mass, and the outlet concentration from the crystallizer is there. And then you do this a third time, So that outlet gets cooled down to a lower temperature. It sits in the crystallizer for its own residence time and leaves the third crystallizer at that concentration. And that would be the outlet concentration from the entire device, or the entire 3 devices, right? And you've sucked out a total of that much mass, and that much mass, and that much mass. And clearly, there's many ways of stepping off these crystallizers, right? You could have reduced the first one to this temperature, and then the second one to that temperature, and the third one to that temperature. And every time you do, then clearly, there's like an infinite number of ways of doing this, even for 3 crystallizers. And then there's an infinite number of crystallizers. You could have done this for 1, 2, 3, 10, 20. So the question is, out of all of these process schemes, what is the maximum and minimum sizes you can generate, no matter how you organize the cascade of the crystallizers? And the answer is, never mind, we formulated a certain problem, never mind what that is, and at the end of it, it's an optimization problem, and at the end of it, you find you get an envelope on the crystal size diagram. So this is the mean particle size of the distribution that you get at the end of 3 crystallizers hooked together the way I described, as a function of the total residence time in the entire cascade. So the residence time is 2 hours. You get a maximum size of 300 microns and a minimum size of 200 microns. If your total residence time is 5 hours, then you get a maximum size of 600 microns and a minimum size of 200 microns and so forth. What you learn, I mean, this is amazingly simple, but what you learn is something that nobody ever figured out before, which is the minimum size is essentially completely independent of how many crystallizers in the cascade. Therefore, it doesn't make any difference whether you have a single MSMPR crystallizer, 2, 3, 4, 10, a PFR, or a batch. They all give you the same minimum size, no matter what the residence time is in that collection of devices. The maximum size, however, depends critically on how many crystallizers you have and what the total residence time in the system is. And all of the particle sizes between the maximum and the minimum are attainable with some different configuration. So you can do this for 2, 3, 4, and so on. And I'm just showing you a sampling of the results. This is the envelope, the attainable region of sizes that you get with 2. This next one is with 3, 4, 5, and infinity. And so what you find from these diagrams, if you're a pharmaceutical manufacturer, and you put together a certain cascade with a certain solvent and a certain solute and so on and so forth, if you want to get particles 50 microns in size, which actually I guess would be down here, there's nothing you can do with this system. You are forced, no matter how you configure it, to end up at least with particles that are on the order of 150, 180, maybe 200 microns in size, which is 4 times too big. Now this is a real problem because you can't formulate tablets with particles that big. So what do? They mill them. The problem with milling is the cost of the milling operation is more than the cost of all the other operations all added together. All of the reaction steps, all of the crystallization steps, all of that pre-processing added together is typically less than the cost of the milling operation. And why is that? These pharmaceuticals are really active. When you dry mill a solid, you make lots of dust and lots of powder, and unless you're really careful, this stuff gets into the atmosphere in and around the plant, and your employees and the local population are breathing in paracetamol at like 500 times the legal dosage limit, and you have a real problem, Houston. So these dry milling operations are performed in a room like and an enclosure like you've got radioactive material in there, and they're really expensive. So there's a huge interest these days in the pharma industry, not just to create continuous manufacturing, but to reconfigure the continuous manufacturing so that you can create particles of the desired size and completely skip over these dry milling operations. And so when you find that the attainable regions of particle size look like this, it's really good to know before you begin, because maybe you should be operating with a different solvent. If you change the solvent, all of these attainable regions change. If you change the temperature, if you somehow change the kinetics of nucleation and growth, you can count for each kind of design value that you select, you can recompute these regions, and now you have a hope of trying to get to a place where your processing manufacturing will produce a particle size that you desire. So these are two different things that you can do with population balances that people don't normally do. You know, the usual mantra with a population balance is you formulate the balance, you solve it for some particular system, you get some distribution, and it's like, gee, look at that. But the really useful thing about population balances, in my opinion, is to interrogate them to try and find some things that you didn't know to begin with. And these are two that I've shown you today, two ways you can use these balances to learn something new. There's a ton of different things that you can do in the future. You can, for instance, ask the question, how can you go, in order to speed up manufacturing R&D, how can you go from the molecular structure, which you identified at the medicinal chemistry level of discovery, how can you take that molecular structure using computation through to crystal structure? How can you then take crystal structure and get crystal shape and crystal growth rates? And how can you take those crystal growth rates and put them into models like I've just talked about to get manufacturing information? So the pharma industry is really keen on this. And a new project that I'm actually starting this fall is a multi-million-dollar project that Eli Lilly have just supported in my lab with cooperation from a colleague of mine, Baron Peters at UCSB, and some people at the University of London in England, where the plan is to be 5 years from now, when we've spent all the money, the plan is we'll have some clue on how to go from the chemistry level, where I'll tell you what the structure of my molecule is, all the way through to now we can go through all these steps I've mentioned, and I can give you some idea about what the manufacturing operations should look like. Will we get there? I don't know. Will I get there? I don't know. I'm probably the weakest link in the chain at this point. But if I survive another 5 years, at least I'll have some idea about how far along that path you can go. I'm pretty convinced within the next decade, the way things are going, that we'll be able to do, not we, I mean that's the royal we, the profession of chemical engineers will be able to go from molecular structure to process structure. And a lot of these things can be done digitally in the computer before you go to the lab. The idea is not to replace laboratory work. The idea is to make it smarter, so that when you finally do go to the lab, you can home in very quickly on a good process scheme. And if you can reduce the process development time for a drug by even 1 year, which I think is really doable, you're talking about potentially hundreds of millions of dollars of incremental revenues. And if you could reduce it by 2 or 3 years, you're potentially talking about billions of dollars of potential incremental revenues. And that's the carrot that makes companies like Eli Lilly interested in knowing the answers to these kinds of questions. So that's it. Thank you so much for your time and attention. And if any time permits, I'd be delighted to answer questions.
Number of nebulous groups. You mentioned kinetic and nucleation rate per group.
Yes.
4 there. You got
The Damkohler number, it turns out, is an unusual one. It goes like the characteristic process time cubed in the numerator. So the normal Damkohler number in reaction engineering, as we know, is the process time in the numerator and the characteristic reaction time in the denominator. So it turns out in this problem, it goes as the characteristic process time, the residence time cubed, divided by the characteristic growth time squared, times the nucleation time to the power 1. So it's a time cubed over a time cubed, but all 3 times are in each Damkohler number. So you don't have separate Damkohler numbers for nucleation relative to process time and growth relative to process. Otherwise you'd need 6, right? Or 4, or however.
It's a combination of
It's a combination of a characteristic process time and a combination of nucleation and growth time.
All right, and if I may, more qualitative statement. So if you are growing only the metastable polymorph,
Yes.
would that arise physically because you're in a CSTR and you're in a situation that you've got enough monomer to grow on that phase, and it's there because of the history of CSTR,
Yes.
but not enough, and because there is none of the stable polymorph, nucleation doesn't get any started, and so you never get any of that material.
No, it turns out that you will get both. So the supersaturation, this is only an interesting problem if the supersaturation is, if the solution is supersaturated with respect to both. If it's only supersaturated with respect to the most stable, then necessarily you cannot get the metastable because the metastable form is undersaturated, right? So the supersaturation, the solution is supersaturated with respect to both polymorphs.
Well, you'd be in a situation where there's enough supersaturation. Well, let's have be enough to sustain the growth of the metastable, but not enough to nucleate, or very slowly nucleate the stable.
Precisely.
And this nucleated washes out.
And that's exactly right. That is exactly right. And the whole trick about the continuous, you said it, the whole trick about the continuous crystallizer is stuff washes out. And that's why the original experiments from Alan Myerson's group couldn't possibly have happened in a batch, because all those crystals are still there. But in a continuous crystallizer, they keep washing out until eventually it finds its lining out point, and then once it hones in on that stable point, it just stays there forever. You'll notice, though, that the time it took for the crystallizer in the experiment to get to that point was like 1.5 shift times, right? It's like 10 hours or more. So if this were batch and, an 8-hour shift, they might never have ever, you might never see this. So it's a really interesting thing that Alan and his group discovered this. I mean, I wouldn't have had the nerve to publish it, frankly. But he was absolutely right on, and he published twice before any theory. I mean, he published in 2014, then again in 2015. Like, wow, this guy has nerve. Without any hint about why this could possibly be the case. But with a simple analysis, you can really establish that it's a real effect.
One thing, we have shown the nucleation code. So you assume that at time of nucleation, the crystals appear with a definite size, and how we arrive at this?
Yeah, the size is 0. So the typical size of a critical nucleus that forms in solution is about 1 nanometer or smaller. So if your size axis is in microns, which it typically is, a nanometer is 1,000th of a micron. So a critical size nucleus is typically 1,000th of a micron. So the assumption in the model is that the nuclei form at 0 size. It's not technically correct, but correct enough that you don't have to be down there fishing around in the nanometer size scale to make everything sort of match up.
I'm guessing that if you want to get these really small crystals for one of these small operations, that what they're going to try to do is they're going to try to increase the nucleation rate without increasing the growth rate
Absolutely.
as much.
Correct.
What are their handles to do that? Because if they just increase the supersaturation,
Supersaturation is
then
one.
they'll probably start getting all beads, right?
Not necessarily. The shape of the crystal is more to do with the crystallography than it is to do with supersaturation. It's not only to do with crystallography, but one of the biggest components in what determines the shape is the crystallography and the solvent. Supersaturation influences the shape by influencing the growth mechanism on the surface. And that will change from low supersaturation to high supersaturation, which in turn will influence the shape as well. But the dominant factors for shape are the crystal structure, the polymorph, and the solvent. The principal handle that you've got is supersaturation and temperature to manipulate the relative, and even solvent. As you change the solvent, you will definitely change the kinetics, the relative kinetics of crystallization, and nucleation, and growth. I don't think, prior to this stability analysis and these particular groupings for the dimensionless groups, people have known for forever that the relative balance between nucleation and growth were important, but they had no idea what that means. I mean, how do you translate that into something quantitative? Well, the quantitative thing are these Demkohler numbers. So now there's a quantitative thing. If you want to get this polymorph, you'd better make your Demkohler number bigger than this. And that means going and making your characteristic times in a certain regime, and that in turn gives you a quantitation about what you need to do for the relative ratio of the characteristic nucleation time and growth time. So the beautiful thing about quantitation is that you've got a target. You need to make the nucleation rate 3 times bigger than the growth rate, for example. All right, now we have a target. How can we do that? Previously, there was no quantitation, so you're sort of fishing around, hoping that as you change temperature, supersaturation, solvent, blah, 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 something good will happen. And that's the beauty, I think, of chemical engineering modeling, is it gives you some pointers about where you should go in the lab in order to get something better out of the experiment.
You might have answered my question, but I would appreciate if you could explain it more. So in slide 20, when you basically show the different phases, the trivial phase and the phase which is thermodynamically stable and also dynamically the beta phase, and the alpha, which is the one I think thermodynamically unstable and dynamically stable.
Right, right.
And you said that in a continuous process we can reach that phase.
Yes.
And that's basically the advantage and the beauty of using the continuous crystallization. I still don't understand why, is there a way that you can reach this condition in a batch system?
Generally speaking, no. And in a continuous system, it works for exactly the reasons we've been talking about. You're manipulating the characteristic nucleation time relative to the characteristic growth time relative to the process time. And that's the beauty of a dimensionless group, right? You can get, once you know the value of a Demkohler number, let's back off for a second and think about a simple chemical reaction, first order, A to B, in a stirred tank reactor. There's one characteristic dimensionless group that tells you what the hell is going to happen. It's the Demkohler number. And it's V times K over Q, right? The volume of the reactor times the first order rate constant divided by the volumetric flow rate. And let's just say that you want to damp-hole the number of 3, which is an absolutely typical value. Well, you can get there by manipulating the volume, or the rate constant, catalysis, right? Or the flow rate. It makes no difference to me how you do it. It might make a difference to you because you might have a tank of a certain size and so you can only change the flow rate, or you might have 3 different tanks of 3 different sizes but you can't change the flow rate, but you can choose the tank. You can do it many different ways, and the beauty of a dimensionless group where you have a target value is there are many ways of getting that same value, and they will all work equally well in the end. Same is true here. If I say we need a damp-hole number there, where this guy is 1 and this guy is 2, you have a whole ton of different ways of manipulating the variables or the design parameters to get you to that point. And now there's the incentive when you go into the lab. We're not trying to do away with experiments, I keep emphasizing that. What we're trying to do is make the experiments more directed. So you can get to that point by many, many different ways in the lab, and the clever experimentalist might be able to do that. In which case, you can get the metastable alpha phase out of your crystallizer all day long. So dimensionless groups are where it's at. Right?
So you have an extra degree of freedom here using your continuous process to basically...
You have a residence time, for instance, that you don't have in... You have a flow rate. You don't have any flow rate in a batch piece of equipment, and that gives you 1 extra degree of freedom in these systems that you will never have in a batch.
Excuse me, the alpha-beta experiment was done in a batch reactor. Would we change in the amount of the beta crystals?
I'm sorry, I mustn't have heard the first part of your question. Can you repeat the first part?
In the previous slide, if the alpha-beta experiment was done in a batch reactor, would it change in the amount of beta crystals?
Are you talking about this slide?
Yes.
If this were done in a batch reactor, you would have ended up only with beta crystals and no alpha crystals, and that would be it. There would be no chance of getting any alpha crystals out of a batch reactor that was seeded with the thermodynamically stable beta phase. No chance. So, I mean, that's what struck us about these experiments in the first place. Like, this can't be true. Because your experience is so prejudiced about all of the things you've read over all of the decades you've read them, that when somebody comes along with a new twist, one's initial reaction frequently is, this can't be right. It's the same thing. So I was advising some people at a pharmaceutical company a few years ago who were developing the continuous crystallization for a particular product. And they were continuously seeding the crystallizer. Why are you doing that? Well, we always seed our batches. Okay. Well, therefore, surely we should seed the continuous crystallizer too. I'm like, no, you don't get it. The whole point is you don't seed a continuous crystallizer. You only seed it to kick it off at time 0 in some favorable initial condition. But at large time, it's going to do whatever it's going to do, because continuous, steady state piece of equipment will home in to its steady state completely independent of the initial condition, and it will only depend on the dimensionless groups that characterize that piece of equipment. So they were seeding continuously, and it was working horribly, which is why I was asked to come and pass an opinion. And it took like 5 minutes to figure out, stop seeding the damn thing and everything will be fine. So, and there's other instances where I've been called in to batch plants, and they say, we're pulling our hair out. This batch crystallizer has 13 hours before any crystals, any nuclei form. 13 hours. Like, wow. Did it ever occur to you to seed it? No, we can't do that. We've never done that before. Well, then you have to wait 13 hours for homogeneous nucleation to take place. But I'm telling you, if you seed it, it'll all be over in 3 hours. So people get stuck in a certain mindset. We never did this before, or we always did this before. And when you want to get them to improve their operations or do something different, they always want to do it like they always did it before. That's my experience. And it's so difficult to get people to change. It's really difficult to get people to change.
I have a quick question. So now understanding that the continuous process is important and has shown a lot of improvement, what do you think about, since there are 7 states, right, that are in the previous model that you guys have?
Yeah.
Have some measurements and do a state estimation in order to somehow understand better how will be the shape of the crystal?
You can certainly do that, and people have done that. Jim Rawlings, for instance, years ago, back in the 1990s, at the University of Wisconsin, had a lovely research program where they were doing exactly that. They were measuring certain things about the system, doing parameter estimation, state estimation, matching things up with models and so forth. That definitely can be done and has been done, but not in the context of the things I've been talking about today.
Okay, but online?
Yeah.
Okay.
Yeah. I mean, they were doing it online. They had this online crystallizer in Madison where they were doing exactly that. But typically when people do that, they're doing it in order to estimate things like the adaptive updating of the nucleation kinetics and the adaptive updating of parameters in other parts of the model. And they're doing that so that they can close control loops and continue to control the process at a given set point in the face of an ever-changing, ever slightly changing form of the mathematical model. You can definitely do that, and it has been done. Yes. We should probably start. I mean, I'm happy to stand here all afternoon. I get paid to talk, but I'm sure people want to go home.
No, we want to go to the coffee also, but there's a question from Dimitris. I think let's take that the last question from Dimitris, and then we'll move to that.
Yeah, I'm happy to stay here as long as you want. Maybe we should talk over coffee.
This is exciting.
My understanding, if I understand well from your stability excursion, if this experiment was continued further,
Yes.
right, there would be another crossover.
No, absolutely not. If this experiment would continue for another 500 years, it would line out exactly where it ended up. This system has transitioned from some initial condition through some transient and lined out at a certain uniquely stable steady state, and it will sit there. If the system is not disturbed, it will sit at that steady state forever. So it's like, like Rayleigh-Bernard patterns, right? There's a certain dynamic where the two plates get turned on to the hot and cold temperatures, and then stuff happens, and after a certain transition you get these hexagonal roll cells, and they just sit there rolling and hexagonally doing their thing forever and ever. It's the same idea.
Well, now would be a good time to stop and thank Professor Doherty for
Thank you for having me.
stimulating talk, and let's thank him.